for blockchain, and which features the world's largest bounties. And I think a lot of DeFi projects are using Immunefi to fund their bounties, and Immunefi has a great community to dig into these bounties and protect the funds from the users of the DeFi projects. So without further ado, I'm going to invite Duncan to present Immunefi.
Thank you very much for that introduction. So I am Duncan. I am CTO of Immunefi. We are a bug bounty platform and security services company. My presentation is going to go over the development practices that you should adopt in order to maintain the security of your smart contract application. So we're going to focus just on Solidity, but not necessarily on Ethereum. We've got a bunch of EVM-compatible blockchains that we're going to talk about. And the format of this presentation is going to be, we talk about a project and what they're selling and what their economic goals are. We're going to talk about the source code of a smart contract that has a bug, and we're going to have an opportunity for you guys to try to figure out what the bug is. And I realize it's really hard. I'll give you a hint if you need it. And then once we've discussed a little bit about what the bug might be, I'll show you the bug. And then we'll talk about what the project could have done as far as development practices to prevent that bug from being written in the first place. Oh, and I apologize about the bright light behind me. It's morning where I am. This is not a filter, I promise. I'm not that vain.
All right. Amazing.
So let's dive right into this presentation. So these are all bugs that were disclosed through the Immunefi platform and were fixed before there was any chance of them being exploited. So we're going to first talk about the world's largest bug bounty ever paid. So the white hat hacker who reported this bug was awarded a $1.5 million bug bounty from Immunefi. Immunefi is a reinsurance marketplace, so you can buy insurance from a company called Nexus Mutual, and then you can stake that insurance policy into Immunefi's pools and obtain yield that way. And then other people can buy a share of your insurance policy at a slight markup, and that's how the yield is generated. The bug here concerns what happens when an insurance policy needs to be paid out. So in particular, there's a smart contract called Claim Manager, and that's the contract that we're looking at. And the redeem claim method is what you call after there's a hack that you have purchased insurance for. The call to check coverage validates that there is appropriate coverage, and if the check passes, they get the correct amount of ether. And I'm going to warn you, this example is really unfair because determining what the bug is here requires a bit of knowledge about the rest of the smart contract ecosystem. So I'm going to show this method that is, it's a cut down version of the actual method, so it fits on one slide. But I'll give you guys 10, 15 seconds to read this, and then we'll discuss. And if you guys figure out what the bug is, awesome. Otherwise, I'll just tell you what it is. Anybody have an idea of what the bug is here? All right, here we go. This is the bug. So the bug is these two lines that have been highlighted in red. The problem is that in Ethereum, on nearly all accounting is done in the unit of the Wei. And this is true of most EVM-compatible platforms as well. The Wei is the 10 to the minus 18 of an ether. And so you have to be very careful when you're converting back and forth between ether and Wei, because if you have a number that you think is in ether and it's actually in Wei, and you try to convert it, you end up with a number that is way, way too large. And that's exactly what happened here. This number is already in Wei. You convert it from Ether to Whey, and you end up with a call that's 10 to the 18 too large. So if you had purchased even a single Ether worth of coverage, you would basically obtain the entire value of the platform. It would be a complete wipeout, because 10 to the 18 is a ridiculously large number. So what could Armor have done here? ArmorFi was originally written for XDAI network, so there were a lot of comments in their source code referring to values in DAI rather than values in ETH. And then they were a little bit inconsistent in their use of Whey and Ether, and in some cases they actually used the unit of the Whey, which is the 10 to the negative 36 of an Ether. They didn't have enough unit testing. Their unit testing didn't actually cover the redemption code path, so you need to make sure that when you write your unit tests, you cover every possible test path. And their comments were confusing. They had comments, at least in one place, marking a value as in Ether when it was in fact in Whey. And if you'd like to learn more, these slides will all be available after this talk, and we have links to postmortems that detail these bugs in great technical detail. So if you're interested in learning exactly what happened and how the bug was found and how the bug was fixed, please check out these Medium links that are at the bottom of every section. So we'll roll right into the next example here. This is PancakeSwap. So PancakeSwap operates on BSC, which is an EVM-compatible blockchain. They operate a lottery. It's pretty straightforward. The lottery is in phases. First, you can buy a ticket, then ticket sales are closed and a number is drawn, and then after the number is drawn, there's a period where the winning lottery ticket can be claimed, and this cycle repeats every 8 hours or so. You buy the lottery ticket in cake tokens, not in BNB. That's a minor detail here, but it trips up some people. And one thing is, in order to avoid having the lottery number be predictable, they use an off-chain source of randomness that's combined with an on-chain random number, and that is used to draw the winning lottery ticket. And a really observant smart contract developer will realize that there actually is already a bug just from this description of how the lottery works. And at the end of the talk, if you have figured it out, I will give you a round of applause if you can tell me what the bug is in this description. So here is the vulnerable method, and I'm going to be honest here, this one's also unfair. The bug here is actually not what is in the method, but it's been left out of the method. So I'll give you another few moments to consider this, and then I will show the answer. All right, are there any questions about this code? Does anyone think that they notice where the bug might be? Okay, so you might notice that this method is called multi-buy, where you can buy more than one lottery ticket as long as you have enough money to buy all of them. There is another method simply called buy that lets you buy a single lottery ticket, and this method was copy and pasted from that one. And the original method actually doesn't have this bug, so there was a mistake in the copy and pasting. And let me show you what that mistake is. The mistake here is that we are not restricting the purchase of the lottery ticket to only during the buying phase. So what's happening here is that there's a transaction that draws the winning lottery number. And when that transaction enters the memory pool, that's the set of pending transactions that have yet to be mined. A sophisticated attacker can run that transaction in their own memory pool and decide and come up with the winning lottery number. And after they know what the winning lottery number is, they can go out and buy that ticket. And if they push their gas price high enough, that transaction that buys the winning lottery ticket will be mined before the transaction that actually draws the winning lottery ticket. And in doing so, you guarantee to win. And since this lottery is about $1 million every 8 hours, that's a pretty substantial source of recurring revenue. And even if you can't guess the on-chain source of randomness perfectly, it's still a pretty good proposition. Has anyone figured out what the error in the description is? I'll go back to this description and give you a second to think about what that might be. All right, we'll come back to it at the end. So, what happened here? So, like I said, it was a copy-paste error. The method in question here wasn't covered or wasn't exposed through the Web3 UI, so people weren't using it. And their unit testing didn't cover the SAD path. So when you're writing a smart contract, it's important that not only do you test that it works the way you want it to work, but also that it doesn't work when you don't want it to work. And that's what they failed to do here. So I'm actually going to pause for a moment here and talk about what do you do when you find a bug in your smart contract and you need to patch it. Because the whole point of smart contracts is that they're immutable. There's no way for you to change a deployed smart contract out from under its users. There's a technique called the upgradable proxy. It uses a opcode in the EVM called delegate call. So effectively what you do is you separate the storage of the data for a contract and the implementation code of that contract. So the storage is referred to as the proxy, and the implementation is referred to as the implementation. And so what happens is that when you try to interact with the smart contract, you interact with the proxy. And then what the proxy does is it uses the delegate call to effectively evaluate the implementation contract's bytecode in the context of the proxy contract. And then fixing a bug in your contract is simply a matter of deploying a new fixed implementation and telling the proxy to use the new implementation. So that there's a great advantage there that you can fix bugs, but there's also a great disadvantage there, which is that they make users a little bit uncomfortable. Because if the project is capable of upgrading the contract, they're also capable of upgrading the contract to something that just says, give the owners of the project all of the money. And so it gives the owners a lot of control to upgrade, but it also gives them a lot of control to do a rug pull attack. In my professional opinion, it's actually very important to use upgradable proxies, because if you don't, you can end up in a situation where there's a bug in your contract and you have no way to fix it. And we're actually going to go through in the fourth vulnerability in this presentation, a vulnerability that was in a contract that was not using an upgradable proxy, and what we had to do in order to fix it. So before we get to that one though, let's talk about a really common bug that exists in a whole ton of contracts that are deployed. And this is where we're going to start using flash loans. Flash loans are a really exciting and very clever financial instrument that's only available on the blockchain. But basically what it lets you do is it lets you take a very large uncollateralized loan, and the contract ensures that you pay back that loan in the same transaction, or the entire transaction fails. So that's pretty clever in my opinion, that you don't need to put up collateral for this. The downside to the existence of this financial instrument on the blockchain is that it basically allows attackers to have arbitrary leverage to distort prices and perform their attacks, as long as, of course, the prices are returned to their original value at the conclusion of the attack. So let's talk a little bit about how yield farming works in DeFi. So a lot of yield farming strategies work like this. A depositor or a farmer supplies a quantity of some underlying asset to the strategy. So this could be Ether, it could be a stable coin, it could even be another yield farming token. And in exchange for supplying that underlying asset, that collateral, they get an amount of the yield token. And then the strategy uses the collateral, uses the underlying asset to produce interest for the depositors. And then periodically, the interest is used to buy the yield token on a distributed exchange, and then the yield token that's purchased is burned, thereby decreasing the supply and increasing the value of the yield token. And that's how you end up with a appreciating asset in that yield token without having to do rebalances or rebases, not rebalances. So in this case, there's a method called harvest, which purchases the yield token using the underlying asset on a distributed exchange in order to provide yield. So because this is such a common vulnerability, this is actually not the literal code of either of these two projects, Vesper or BT Finance. This is just an example code. But the underlying mechanism is functionally the same. So first what we do is we withdraw token A, and token A here is our underlying asset. It's going to be Ether, some stable coin, whatever. We compute the amount that we're going to swap for. So we do a swap on that distributed exchange where we take the reward token, the underlying asset, and we swap it for some of the yield token. And then in this case, we deposit the token B back into the strategy contract. It could also be burned. That implementation detail is not super important here. And I will admit again that this is a bit of an unfair example because what the bug here is not what is present, but rather what is missing. Although I think this one is a little bit easier than the last one. So now I've talked at you at length here. I'm going to give you a little bit more time to consider this smart contract, and then we'll move on to the solution. All right, let's open it up for questions. Does anyone have an idea of what the bug could be here? So I told you that it does involve flash loans, so that should tell you something about the nature of this attack, is that it's not so much a logic error as it is an economic error, or perhaps a permissioning error. All right. So I've highlighted in red the code that needs to be added in order to prevent this attack from working. So the problem here is that this harvest method can be called in the middle of a flash loan. So while you're in a flash loan, because that flash loan basically gives the attacker arbitrary leverage to distort financial markets, distributed exchanges, they can force the call to harvest to purchase the token at a very unfavorable price, even if that price is very far off the real market rate for that token. So I've detailed here at the bottom the steps for this attack. So first what you do is you flash loan the underlying token. So that's going to be Ether or some stable coin. And then you swap the underlying token for the yield token. And so what this does is this massively inflates the price of the yield token. It makes the yield token very, very expensive in terms of the underlying asset. So then when you call harvest, keep in mind this is in the middle of the flash loan, so the price is distorted. When you call harvest, harvest does a swap. It buys the yield token using the underlying asset. But because the yield token is now very expensive, the strategy contract doesn't get as much of the yield token as it was designed to get. So then, after harvest is done, and it's done its swap at a very unfavorable price, you reverse the swap that you did in step 2. So you'd swap the yield token that you got during step 2 back for the underlying token, restoring the price to its original value. And when you do that, then when you swap back, you get back out a bunch of the original asset. But because there was a harvest that happened in the middle, you're going to get back more of that original asset than you put in step 2. In fact, you're going to get out the majority of the harvest asset, so the asset that was supplied to the distributed exchange during that harvest. And then, of course, at the end, you return the flash loan, and any surplus token or any surplus asset is yours to keep. In practice, this allows you to steal about 2/3 of the harvest yield, the harvest returns, which in the case of a lot of these strategies can actually be very substantial, can be on the order of hundreds of thousands to millions. So the one strategy here is, of course, to add the only owner modifier, so that prevents this method from being called by anyone except the contract operator. And another solution is to just require that the message sender be the same as the transaction origin. So the transaction origin is always an EOA. That's a wallet address, not a smart contract. So it's an actual human. And if you required that the caller of this method be an EOA, then you know that you're at the top of the call stack, that there's absolutely nobody between you and that wallet address. Another mitigation, it's not actually a fix, is to simply call harvest very frequently. Because flash loans and flash swaps like this, they require a fee, they require a liquidity provider fee. If the amount that is harvested is less than the fee that would be charged in order to steal the harvest, it doesn't make economic sense for that harvest to be stolen. And so And so by adding this line in red, require sender equals address this, what you're doing is you're saying that we only accept flash swaps from ourselves, where we are ourselves the initiator. And in that case, we know that the call data that's being supplied can't be malicious because we're the one that supplied it. So the impact here was that you could use that attacker-controlled call data to call another method in this contract that could ultimately result in liquidation of another user's position and leaving them holding a very large quantity of some worthless token that you created just for the purpose of this attack. Now, I told you that I would explain an attack, what you do to mitigate an attack where there's no upgradable proxy. So this attack didn't have an upgradable proxy, and the severity of the attack was actually quite high. There's a thing in Ethereum called an ERC20 token approval, which basically says, I trust this contract and they are allowed to spend my money. So not only could this attack spend or steal all of the money that was in the contract directly, it could also steal all of the money in any other address that had approved the vulnerable contract to spend their token or to spend their asset, which in this case was actually extremely large. There was a very large amount of money locked up in those contracts, or in those addresses, I should say. So the end result here was that we had to hack all of the users ourselves because there wasn't any other way. So what we did was we set up a bunch of contracts and we used the Taichi network to submit smart contracts without them having entered the public mempool. And we stole all of the money from all the users, and then we gave it right back. And I realize we are now at the top of the hour, and I think I have 10 minutes left here of your time, so I will go quickly through this next and final vulnerability, unless we would like to open it up for Q&A and cut off the talk here. Okay, I'll go through the next vulnerability. So, this is sort of the same as before. There wasn't enough validation. You need to make sure you whitelist absolutely everything. The postmortem here is very exciting. It was a very exciting 48 hours for me. I recommend that you go read it if you're interested in what goes on behind the scenes when there's a crisis like this. Okay, so this is Fei protocol. This is probably a more recent, a more topical vulnerability. You may have heard that Fei protocol developed an algorithmic stablecoin using using buy incentives and sell penalties to maintain the price peg. And then, of course, they also make use of this thing called protocol controlled value, and it's all very cool. I encourage you to go read their white paper. And in this case, the bug is in the buy and sell incentives. Essentially, when the price of the stablecoin is below the peg value, and that is 1 coin per US dollar, when the price is below that peg value, there is an incentive to buy to push that price back up towards the peg, and there's a disincentive. There's a penalty for selling, which moves the price further down below the peg. And in this case, the problem is that if you buy, you get rewarded. But then there's a very clever way that you can sell back down to the original market price and not get penalized. And so the original design is that the buy and the sell penalties are exactly balanced, so that you shouldn't actually be able to obtain any sort of profit from that. But because you can bypass the sell penalty, you can use the buy to increase the price, get that reward, and then when you sell and decrease the price, there's no penalty. Using this requires some knowledge, deciphering this bug requires some knowledge of how Uniswap swaps actually work under the hood. So since I've had this slide up for a while I'm talking, I'm going to bring up the source code of the relevant Uniswap methods. So there's two methods here that are important. There's swap and there's update, and so those are what are on the screen right now. And I'll give you guys a few more seconds to read those, and then we'll go and ask again, have you found the bug? I'll give you a hint here. In this case, the problem is a desynchronization of a balance between what the balance really is and what we think the balance is. All right, so here's the vulnerability. The problem is that the buy and sell penalties and incentives are computed based on the reserves of the Uniswap pair. And the reserves of the Uniswap pair are the amount that the pair thinks it has. And it's always required that at the end of a swap that those numbers go up. The problem is that because it's computed based on the amount of money the pair thinks it has and not the amount of money that it actually has, is that you can have the pair think it has less, or that has less of an asset than it actually does. The reverse, of course, is never true. It always knows that you can't ever have it have less than it thinks it has. It can only ever think it has less than it actually does. And the problem there is that by using that gap, you can distort the price that the pool thinks it has compared to the price that it actually has. And so what you can do is you can buy, using a flash loan, you can buy enough of the stablecoin to push the price above the peg. And you do that in a swap, and that updates the reserves. And then you can trickle the money back into the coin, back into the Uniswap pair, without updating the reserves, without updating the price. And so if every transaction that you trickle the money in doesn't bring the price below the peg, even though the balance is updating but the reserve is not, you won't get burned. And then of course at the end you do a swap to get back to the original asset, and you end up making a nice tidy profit. And in this case, I believe we computed that the profit was about $3 million US. And of course this attack is repeatable. What's the problem here? They didn't explicitly define their system invariance. So there's some really good tools out there for you define that these two numbers should always be equal, and if you manage to find a way to make them not equal, then that's a bug. There are tools that are called fuzzers that are used to find ways to violate that assumption. The best one out there, I think, is called Echidna, produced by Trail of Bits. But I am open to hearing about other fuzzers because I always like learning about cool new tools. So yeah, define your system invariants, check those invariants, use a fuzzer. If you want to learn more about this vulnerability, I recommend reading the postmortem here. Make sure you always use an upgradable proxy, whitelist everything, check your invariants, and of course, get an audit from a reputable auditing firm. And of course, the last bastion of defense against black hat attacks are bug bounties. Each of these could have been and probably would have been exploited by a black hat if it weren't for the fact that there were substantial financial rewards for disclosing these vulnerabilities instead of exploiting them. So if you're interested in launching a bug bounty program, receiving advice about which auditing agencies to use, or receiving a full spectrum security audit. Immunefi does not offer smart contract audits, but we can put you in touch with a firm that does. Please get in touch. We are on Telegram, Discord, email. We have our own platform. There's all sorts of ways you can get in touch with me. And thank you very much for your time. And with my remaining 3 minutes, people can ask me questions.
Thank you, Duncan. Yeah, it's a super interesting talk, and we will wrap it up and put up the video on Bilibili and on YouTube after 3 days. I think the talk gives some really good examples of some of the major vulnerabilities happening in recent projects, and yeah. So let me check if there are any questions. So one of the questions is like how exactly people can interact with Immunefi platform, and how to post the bounty.
Yeah, so we have a bunch of different ways that you can interact with us. Like I said, we're on Telegram, Discord, Keybase, Signal, but the best way is to get in touch is to email team@immunefi.com, which you can find plastered all over our website if you go to immunefi.com, and we will help you set up your bug bounty program. That's our job. We walk you through a bunch of best practices, standard templates, and of course we tailor your bug bounty program to your specific security concerns.
Okay, so the next question is, does the Immunefi only focus on DeFi?
We only focus on DeFi, but we have a pretty broad interpretation of that. So blockchain projects, if you're launching your own L1, distributed exchanges or centralized exchanges, we're happy to help you out. Projects that are launched on a smart contract platform like the EVM, yeah, really anything like that, we are happy to help you out, as long as you're in the blockchain space.
Cool. Yeah, so the next question is from the community. I see. So you talk about the it's a good practice to use proxy contracts, and so that the contract is upgradable, so if you find any bug, you can upgrade the contract. But people are concerned that with a proxy contract, you will there is a centralized control. But on the other hand, if your smart contract is not upgradable, how do people normally fix it? Any practices related to this one?
Yeah. So one solution that people use to get rid of the concern about centralized control is you have the upgradable contract controlled by a DAO. But if you can't use an upgradable proxy and you have to just deploy the contract bare, if you find a bug, the way you mitigate it is by either encouraging people to stop using it, hacking it yourself and then returning the user funds, or trying to find some other way to work around the bug. And it's really difficult, and it depends on a case-by-case basis. So Immunefi does actually provide a service for when a bug is encountered in a contract that isn't upgradable. We call it our War Room product. And if you're interested in that service, please get in touch. There's a deposit, and then of course, if you have to activate the War Room, we put you in touch with all of the best experts in DeFi, and we work around the clock to safeguard your contract.
Okay, that's interesting. So question for myself: what is the Immunefi community consisting of right now? Because I think you have the platform, right? So there is a community of developers or web hackers who can look at the smart contract and look for bugs. So can you tell us a little bit about your community and what kind of people are in the community?
Yeah, so our community is pretty broad. It's, as you say, it's almost entirely white hat hackers, people who are, already well experienced, all the way down to people who are just starting out, people who are experienced in web bugs, people who are experienced in smart contract, or people who are in web and looking to move into smart contract. We have some of the best names in the space. We have people who work for top-tier auditing agencies who look for bugs in their free time. We have people who are themselves accomplished smart contract developers who sometimes they, in their free time, they look for bugs in other projects to claim those bug bounties. I hope that answers the question.
Yeah. So that's really cool. It's an amazing talk, and we'll post the talk a little later, and we will definitely introduce the service to our community, our partner, probably because we're also rolling out several products. We have been rolling out a few products, and we're rolling out several features, and we'll definitely try to use Immunefi to safeguard our product as well. So
excellent.
Later. Thanks, Duncan, for introducing Immunefi, and I think it's amazing to present this in front of Chinese community, and people are actually loving this kind of content. So stay in touch, and thank you very much.
Happy to help, and if you're interested in this sort of thing, we'll be pushing out a lot more content like this. Follow us on Twitter, Medium, you name it. We'll get the information to you.
Cool.
Thanks.
Thank you.